In modern web infrastructure, servers generate millions of log entry daily. These logs contain critical information about traffic patterns and user behavior, security threats, DDoS attacks, bot traffics like, and system errors and performance bottlenecks and resource utilizations and bandwidth consumptions. And the industrial challenge is this traditional log analysis tool often struggle with processing large volumes, maintain data integrity during concurrent operations, and providing reliable, reproducible results and ensure code maintainability and testability. For that, our solution is we build a pure function log analyzer using Haskell that demonstrate how functional programming principles solve challenges through purity, immutability, parallel processing, type safety, and compatibility. Let's quick demo our project. First, we need to build our project by stack build. Stack is the build tool of Haskell, and we need to execute the sample data. And here in the data, there is 3 files. The sample data is for the some sample data we got for the analyze. Here you can see there is a 20 lines of data. Access log is complete all the access logs we got from the Apache and Nginx server. And first we execute this sample data, and after the executing, you can see it's generate the full reports. It shows how many files it's read and how many it's passed successfully, and computed statics by status category, and found top IPs. Here are the top IPs, and detects any distributions and flags any anomalies. In here is no any anomalies, that's why it has no any anomalies. And now let's run the full data. In here it's get little time. There's thousands of lines in that access.log. In the dataset we got from the Kaggle, here is the logs. These are the sample logs that we got to execute. Yeah, now you can see it's already executed. In that's full report generated. In here you can see the top IPs and error distributions, and there's so many anomalous detections in that sample logs. Here you can see the sample full report in there. Next we go to the server log analyzer architecture. The green areas, these are the dirty parts of the system that interact with the outside world. And the green areas is the sanctuary of our logic. It is pure, meaning the functional behave have predictability. That means same input, maybe same output. And there is no any side effects. This makes system incredibility, testability, and readability. In the impure input IO layer, Apache, Nginx logs the raw data sources. The file read by utilize lazy IO. This is crucial for the log analysis. Instead of loading the 10 GB logs for the RAM, which would crash the server, lazy IO streams data on demand. We conceptually treat the file an infinite list of characters that are read only. The log parser module acts as a AR log. It takes dirty raw strings and validate them and convert them into our internal domain model. And the pure functions core, the brain of our system, the log entry algebraic data type, this is our schema. It is immutable. Once a log entry is created, this cannot be changed. This is eliminate a massive class of bugs known as race conditions, because multiple reads can read this data without fear of changing the under their feeds. And parallel analyze pipeline filter, a higher order function that stripes our noise, and transformation, convert the data into the shapes, and aggregation, and this indicate a strict left fold. In Haskell, this is performance optimization to prevent memory leaks during the large accumulations. It ensures we calculate the running total immediately rather than building up a massive chain of to-do calculations. And sessionization, function probably doesn't use for loops, it uses recursion to traverse the list of logs and group action by user session. And evaluation strategy, our core is pure, no side effects. We can parallelize execution trivially. We simply give the compiler the hint, the bar buffer, to process the chunk of the list of the parallel. We gain multi-core performance without writing a single log, mutex, or semaphore. In the analyze result ADT, this is represent the final report data. It is marked strictly to force the lazy IO to actually execute. This layer handles the side effect of writing the disk or printing the console logs. And when you're thinking about this architecture, this way readability by isolating the IO in the blue color and for the logic green color. We can unit test the entire system pipeline without need mock files or database, and the concurrency strategy allow us to utilize all CPU cores to heavy logs processing with zero disk deadlocks. And maintainability, the use of ADT ensures the invalid states are in representable. We can't accidentally create a half-pass log entry. And this is our full architecture of the server log analyzer. Now let's deep dive in our project, how purity, immutability recursions apply in our projects in data types.hs. First, let's talk about purity. Look at this function. This is pure function. It means if you give it 200, it always returns success every single time. This is no hidden state, no global variable it might read from. Same input, give same output. This make our code predictable. Just check input is output. I can replace status category 200 with success anywhere in my code. It will work exactly same. This is called referential transparency. It is like a mathematical equation. Here is another example. Our password. Notice how it used pattern matching of each case in handle explicitly. The last pattern other catch anything's unexpected. So pass methods is unknown instead of crashing. This is function is total. It handle all possible inputs safely. No exception can be thrown. And many things how this make code safer. No crash from unexpected input. Easily to understand each case in right there and compile checks that handle all patterns. And now look at our main passing function pass log line. This type signature says string, maybe log entry. The maybe tell us passing can fail. It returns just log entry on success, nothing on failure. Instead, we use the do notation. If any step fails, pass timestamp and pass method or read maybe, the whole function return nothing. This is maybe monad or elegant error handling without try catch blow. When we think about immutability, now let's talk about the immutability. Look at our count by level function. Focus on this line m.insert insert plus category 1 ACC. This is does not modify the map ACC. It creates a brand new map with the updated count. This original map is never changed. We are building up a new value, not mutating old one. This when you're thinking why this is safer, no mutation bugs and thread safe and predictable. Here's another example of top IPs. Top IPs. This is use function composition with dot operator. The IP into the map and m dot to list convert to the list creates a new list and sort by sort the count creating a new sorted list and take an n top n create a new list. For every step create a new data. The original entries list is completely unchanged. Though we can use entries again safely. It hasn't been modified. No defensive copy needed and data can be shared freely. Looks at how we use in our main pipeline. We use entries twice, one for the processor's logs and one for the compute anomalies. This works perfectly because entries is immutable. Neither function can modify it. In fact, we could run both functions in parallel without any logs or synchronization. This is the power of immutability and safe parallelism for free. And let's talk about the recursion. Look at our split session function. The line one, this line one is the base case. If list is empty, return the empty. This stop the recursion, and the line 2, this recursive case, the pattern destructures the list into the X and tail exits inside into the go helpers. If times gapped exceed the timeout, save current session, start a new one. Otherwise, add entry to the current session. You will notice we use fold backtick a lot in our code. It is itself a recursive function. Each process, each element one by one, accumulating a result. Instead of writing map and for loops like this. Look at this line in our session function. This little annotation used into the power buffer 100 secure makes our code in parallel. We didn't need to add a lock or mutexes. Do not need to worry about the race condition and no need to write complex synchronization code because our code is immutable and our functions are pure. Therefore, multiple threads can be safely read the same data, no shared mutable states. Therefore, no race condition.